We've already seen that truth tables are organized ways to see all of the possible true or false values for compound statements. In this video, we examine a few more applications of these truth tables. Specifically, we'll use them to look at statements, compound statements, and decide what type of statement they are. So we have a few new terms, tautologies and self-contradictions. A tautology is a compound statement that's always true, regardless of the truth values of the simple statements that make it up. And a self-contradiction is a compound statement that is always false. Well, how can that be true, especially if we don't even know if the simple statements are true or false? Well, here are two examples. If you look at the statement, it will rain today, or it will not rain today. It doesn't really matter if it does rain today or if it doesn't. Regardless of which situation we have, that is a true statement. It must be one of those or the other one. So there's no situation in which that compound statement is false. It's always true. So that would be an example of a tautology. If you look at the second statement, today is Sunday and today is not Sunday, well, it doesn't actually matter if it is Sunday or isn't. In either of those cases, this is still a false statement. It can't be both Sunday and not Sunday at the same time. So that example would be a self-contradiction. So if we have a longer statement, like a compound statement with maybe more components or more simple statements to it, it can get tricky to decide if these things are always true or always false, or if it's neither. Sometimes we've seen examples of statements that it sort of depends. So that can be a purpose for truth tables. We can use these to decide if a statement is a tautology, a self-contradiction, or just a normal statement that's sometimes true and sometimes false. So let's take a look at an example. We have the statement P and Q implies P. Right? So if you haven't already, if you're not comfortable with making truth tables, go back and watch those other videos. I will assume at this point that you do know how to make these, so we'll kind of move quickly through constructing this truth table. Alright, so I've laid out the tops of the columns here. I've got columns for the variables and then one for each of the connectives, and we'll start with the normal setup. Okay, and then we'll follow the rules for the connective and for conjunction. So in this first row, true and true is true, true and false is false, false and true is false, false and false is false. Okay, and then next we'll follow the rules for the conditional connective. So we're looking at the P and Q column first, and then that, and we're seeing if that implies this P column. Okay, so true implies true is true. And the second one, remember we're reading this backwards, so we would have false implies true, and that's true. And then false implies false is true, and false implies false is true. Whoops. I said true and wrote false. Okay, so this is what you'll see. So notice that the very last column, this is the one for the entire statement, and in every case, the truth table is showing us that this is a true statement. So regardless of whether P and Q were both true, or one of them was false, or they were both false, this statement still turns out to always be true. And that's very clear when we look at the truth table, and in some cases it may not be as clear if we actually put some words to this statement and we're speaking this out loud. Alright, here's another one. We have a compound statement, P and Q and not P and not Q. Alright, so we'll do a truth table again to decide. Alright, so we have our setup. We've got columns for P and Q, then the negations. So I'm doing a column for each connective and following that hierarchy. And then we have our typical first two columns for P and Q. Alright, and then we go through and do the rules for negation. So we'd have not P would be false, false, true, true, and not Q is false, true, false, true. All right, next we do the rules for AND with the P and Q columns. Okay, so I would have true and true, true and false, false and true, false and false. And then same rules, but this time looking at not P and not Q. So those two columns. So we'd have false and false, false and true, true and false, and true is the only one that's true. Okay, and then finally the rules for AND again, but with the two columns that we just did. So true and false is false, false and false, false and false, false and true. So here we see something different. In the very last column we have all falses. So in other words, it doesn't matter whether P and Q were both true, both false, one of each. In any case, the statement that we made turned out to be false. So this statement is always false, so this is an example of a self-contradiction. And then it could be neither, so what you would see there, you would just see a last column that has a mix of some trues and some falses, and then that statement would neither be a tautology nor a self-contradiction. Here's another use for truth tables. We can use them to decide whether or not two statements are logically equivalent. In other words, are they the two different statements? They may sound a little bit different, maybe one's reworded, but are they saying basically the same thing? Right, so two compound statements are logically equivalent if and only if they have the same truth values for all possible combinations of truth values for the simple statements that compose them. Right, so that's a mouthful, but basically if we were to make a truth table and we were look at all of the possible cases for each statement, so we would go to like the last column for each statement, and let's say we had like true, true, false, false for the first one, and then let's say that the second statement matched that, true, true, false, false, okay, then the P's and Q's, right, whatever they were, true, false, we don't know, but in either case, the end statements that we made had the same truth value. Okay, so typically you would do this with two statements that are sort of talking about the same thing, but you could have two logically equivalent statements that do sound quite a bit different. So we could make them really complicated, maybe something so long like you probably wouldn't say it in real life, but we could still decide if it's logically equivalent or not. But typically we'll look at examples that maybe are a little bit shorter and we just want to check things that we actually would say in everyday life. There is a symbol for logically equivalent statements, and it's like an equal sign, but it has 3 bars to it, and that means that the two statements have the same truth values in all cases. Here are 2 examples. We have one statement that says, I don't want to go to the movies or the baseball game. And we know that that person means I don't want to go to the movies and I don't want to go to the baseball game. So it's just a slight rewording, but the meaning is still the same. So if we were to look at, the true or false values for these things, if this first statement is false, then the second statement is also going to be false. And if the first one's true, the second one would also be true. Okay, so we're going to use a truth table to decide if the statement, if P then Q, is logically equivalent to if not Q, then not P. Right? So we're going to make one truth table, and here we're assuming that P and Q do represent the same simple statements. So we're going to combine everything into one truth table, and the last 2 columns are always going to be like your last two statements. I guess you could reorder it a little bit. Maybe we'll do an example that's like that as well. But by the time you have finished, you should have a column for each of these 2 statements. All right, so we'll continue on with the columns for P and Q, and then follow the hierarchy for connectives as we've been doing. Okay, so I would scan both statements, and I just see 2 simple statements, P and Q, so we've got columns for those, and then columns for the negations. Now here I've switched it because it is, for conditionals, it's a little bit easier to have the premise on the left and the conclusion on the right, but you could also do not P and then not Q instead. All right, and then in each statement, if I'm following the hierarchy, in this first one, there only is one connective, so normally that would go like after P and Q, but I've just moved it over a little bit so that I could get my negations in there first. All right, and then in the second statement, we just need to make sure we do the negations before we do the conditional. All right, so let's fill it in. So we have our normal columns for P and Q, and then we have the negation of Q, so false, true, and the negation of P. Okay, and then follow the rules for conditionals. So if P then Q, so true, if true then true, that's true. If true then false, that's false. False, if false then true is true. And if false then false is true. All right. And then the second one, so I'm following the rules for conditionals, but this time using the not Q column and the not P column. Okay, so my first one would be if false then false, that's true. If true then false is false. If false then true, that's true. And if true then true, that's true. Okay, so now I want to compare, so you find the two columns that have those two statements, and you just check down and make sure that they have the same truth values in each row. So true, true, false, false, true, 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 true. So everything matches, so those two statements are logically equivalent. Okay, so instead of and, I could use that symbol in the middle. Okay, one statement is logically equivalent to the other. Here are two more. These are the famous ones. These are called De Morgan's laws for logic. And these are pairs of equivalent statements that are, we just use these quite a bit, and they also simplify things a little bit when we're trying to negate and or statements. So that might be another reason they've been highlighted as important here. The first one just says symbolically what my first example was. Okay, so this is the negation of an or statement. So the example was I don't want to go to the movies or a baseball game. Right? And it's a little bit harder to hear when you have this in words, like where the parentheses are. But it was sort of implied there that he, whoever this was, I don't want to go to either of those two things. So it's like not movies or the baseball game. Okay? And that's saying the same thing as not P and not Q. Or in other words, I don't want to go to the movies. So that's the opposite of wanting to go to the movies. And I don't want to go to the baseball game. Okay? And then the second one tells us how to negate an and statement. So in other words, it's the same thing if you say not P and Q is the same thing as saying not P or not Q. So let's talk about an example in words. So let's say that we're baking an apple pie. So we would say for the apple pie we need apples and sugar, and obviously many other things, but maybe those are the two prime ingredients, right? And if we're saying that we don't have this, okay, if I don't have that for the recipe, then what I'm really saying is that either I don't have the apples, okay, no apples, or no sugar. And then of course it could be true that it's both of those things. Maybe there's no apples and also no sugar, but it doesn't have to be. So if you need these two things for the recipe and you don't have either one, then you can't really say that you do have apples and sugar. Right? So when you want to say the opposite of an and statement, it's got to be the opposite of each piece of this, but then just with the word or in the middle. It doesn't have to be both of those two things. Right? Or maybe another weather example. Maybe you're trying to say the opposite of that it is, like, let's say, cloudy and rainy. Right, well, what's the opposite of being, or the negation of cloudy and rainy? It could either be not cloudy or not rainy. So I will leave this for you to do as an exercise, but one thing you could do now is to use truth tables to just double check and make sure that these two statements are saying the same thing. Right? So if we looked at maybe the second case, to make a truth table to decide if those are the same, you would set up columns for P and for Q, right? And then I do see, let's see, we'll go with the first statement first. So if you follow the hierarchy, you would need to do the AND statement first, okay? And then you would do the negation of the parentheses. Okay, so AND came first because it was in parentheses. Okay. And then in the second statement, following the hierarchy, you would do negations first, okay, and then you would do the OR statement. Oops, not P or not Q. Okay, and then to decide if these are logically equivalent or not, you would look at the two columns that represent those two statements, so this one, and then you would just look down at the true and false values and make sure that they match in both cases. Alright, so a quick summary. In this video we talked about using truth tables to decide if statements were tautologies, always true, self-contradictions, always false, or neither. And then we also used truth tables to compare two statements and decide if they were logically equivalent or not.